Welcome to this R and Pharma workshop on this beautiful Wednesday morning. Now kicks off officially our third day of workshops of the R and Pharma conference. If you haven't registered, we'll put the link to that in the chat box. With that, I'm going to go ahead and just turn off my screen share and pass it over to Eric.
Thank you, Phil, and certainly welcome everyone. This is a massive turnout, but we are so excited for you to be here, as Phil said, on this third day of our Pharma workshops. And it is always one of the most exciting times of the year for me personally. We get to learn so much from the R community within the life sciences space and others that are really interested in sharing their knowledge. And today is certainly no exception to that. So as Phil mentioned, I'll be one of the TAs kind of monitoring the chat for questions that will pop in from time to time as we get opportunities. But let's introduce our instructor for today, Nicola Rennie, who is a lecturer in health data science based within the Center for Health Informatics, Computing, and Statistics at Lancaster Medical School. And one of her research interests is indeed machine learning. So she is a very pronounced expert in the field of machine learning and the tidymodels that you'll be learning about today. And I'm also especially excited to have Nicola here because she has been one of the more frequent contributors to another project I'm involved with called R Weekly. So you will often see her blog posts featured as highlights practically every month that we've been curating. And she's been such a fountain of knowledge to us about all the realms of data science, especially with R. So I think that'll do it for my intro here. So Nicola, I will pass it along to you to kick us off.
So welcome to the Introduction to Machine Learning with tidymodels workshop. In terms of what to expect during this workshop, it's going to run for 2 hours. There's going to be a combination of some slides with a bit of me talking and kind of explaining the models that we're going to be fitting. I'll then run through some live coding examples and we'll talk through the tidymodels code. As Phil mentioned, there's going to be a couple of Zoom poll quiz questions. And there's also some exercises for you to participate in. So if you want to code alongside me when I'm going through the examples, feel free, but also feel free to just sort of watch and then sort of have a go at the exercises instead. I do encourage you to ask any questions in the chat throughout. And I hope that you end up with more questions than answers after this workshop. Machine learning is a really big topic. Tidymodels is a really big topic, and we can't cover all of it within 2 hours. So I hope that this kind of inspires you to get started with machine learning and tidymodels. If we don't manage to get through all of the questions that you have in the chat, I will kind of write up the answers to some of those questions as a blog post afterwards to hopefully answer your questions. In terms of workshop resources, everything you need for the workshop is on the Posit Cloud space. So all of the sort of code and examples are there. The code is also up on GitHub as well. And there's a copy of these slides online as well. I think you've already got the link to them, but that QR code will also take you to the slides if you want a copy for yourself. So a little bit about what we're going to be looking at in this workshop. We're going to be using 2 different data sets. So I'll be using one data set for all of the examples that I do, and that's going to be looking at clinical records for heart failure. So we have data on different patients, their sort of characteristics, and then a binary column looking at whether or not they had heart failure. And then in the exercises that you're going to be having a go at, we have some clinical trial data. So this is clinical trials for people who had a stroke and then were prescribed either a 6-month program of exercise or a 6-month program of relaxation. And the idea is to model whether or not that increased or decreased the likelihood that they had another stroke within 6 months. So both of these datasets are in the data folder on the Posit Cloud space. They are tidier versions of the original dataset. So there are links to the original data if you want it, but I've done a little bit of cleaning and tidying up for you because it's not a workshop about dplyr and tidyr. If you want the script for the data cleaning, they are available on GitHub if you want them. Okay, so a very quick Zoom poll. Have you done any machine learning in R before? So I'm hoping that there's a Zoom popping up on your screen. So if you can let us know whether you might not have done machine learning in R before at all. You might have done a little bit of tidymodels before. You might have done it with Carrot, which is another sort of R package for machine learning. And you might have done it specific models in R before with some other packages. All right. Okay, so let's actually get started with thinking about tidymodels. So the first kind of section of the workshop is going to focus a little bit on what are all the things we need to think about before we actually fit some models. Okay, so you can see that the Zoom poll here is that most of you haven't done any machine learning in R before, and the rest are kind of split before. So that's great. So this will be a proper kind of introduction to both machine learning and an introduction to tidymodels for both of you, for both groups of people. So first, probably explain what exactly tidymodels is. Essentially, it's a collection of R packages for statistical modeling and machine learning. And you might guess from the name that it does follow the same sort of principles as the tidyverse. So it's a kind of collection of packages, and each package is for a sort of specific part of your machine learning workflows. And it follows those nice, sort of really nice user-friendly principles that tidyverse has. So functions are named well, they do specific tasks. You can install all the core tidymodels packages with install.packages, and that installs the 8 core packages. So a little bit like the tidyverse, there's these 8 core packages, but there's also other extension packages as well. And you'll see a couple of them during the workshop. So you have RSample for sampling and splitting your data. We have recipes for some of the pre-processing steps. You have Parsnip, which is for sort of actually specifying the models. Yardstick for evaluating model performance. Broom for sort of tidying up the output from some of your models. Workflows for actually making model workflows. Tune package for tuning hyperparameters. And then the dials package is also for tuning hyperparameters, but in a sort of more specialist way. Some of those words might not have made sense to you. That's absolutely fine. I'm hoping that by the end of the workshop, you will have a good idea of what most of those words mean, and we'll probably be using most of these core packages today. I also want to sort of mention what is machine learning, because I think everybody that you ask will have a slightly different definition of what exactly machine learning is. So I'm going to use this definition for today. Some people use sort of AI and machine learning and deep learning as interchangeable terms. To me, machine learning is a type of artificial intelligence, and deep learning is a specific type of machine learning. And when we talk about machine learning, we're talking about learning things from data. Most of the time, we're interested in doing things like making predictions or sort of classifying observations. So what we're going to be doing today sort of sits within this little bit here. So in the machine learning framework, but not deep learning or neural networks today. In terms of types of machine learning, we usually split them into 2 different types. So we could have supervised learning. So that means that we need to have some labeled input data. And the types of problems that we usually want to be looking at with supervised learning are things like classification or regression-based models as well. For unsupervised learning, that means that we don't need any labeled input data. Okay, so this tends to look at methods like clustering or association rules. There are other types of machine learning that don't fall into the supervised or unsupervised learning. So you might hear terms like semi-supervised learning or reinforcement learning. We're not really going to pay attention to those today because they're just a little bit more advanced. And today, actually, we're mostly going to focus on supervised learning. And we're going to look at mostly classification problems, although you'll see how you can switch between classification and regression problems within tidymodels. So before we actually start fitting models, there's going to be a couple of things we need to do to our data. Okay, so I've kind of gone through the process of tidying your data and getting it into a nice format. But even after that, there's some other things we need to do. And the first thing is to start thinking about training and testing data. So we want to split our data into two groups, training and testing. The training data set is going to be used for model development. Okay, so this is where we're going to do things like pick which values a parameter is going to take in our model, for example. Okay, so if you think really simply about something like linear regression, you'd use the training data set to figure out what a coefficient is, what the value of the coefficient would be. After we've sort of developed our model, we can then apply it to the testing data set to evaluate how well our model performs on data that is never seen before. Okay, so it's really important that none of that testing data goes into the training process at all. They're always completely separate. However, when we're using the training data and we're trying to build our model and choose our parameter values, we can't always learn every parameter from the data. Okay, so in simple linear regression models, you can always figure out, you can calculate directly what the value of all of those coefficients should be from the data that you have. For all of the models, in fact, that we're going to look at today, that isn't true for every parameter. So we have these things called hyperparameters. And what we essentially need to do here is try a bunch of different values and see which ones work best. And there's a couple of different ways to do that, but one of the most sort of common ways to do it is using k-fold cross-validation. Okay, so what you do here is you take your training set of data and you split it up into different folds. You fit your model with a particular value of your parameter to, say, 90% of your data. You see how it works on the remaining 10%, and you do that a bunch of times until you pick the best value of that parameter for your model. Okay, and you'll see how to do this in tidymodels. Okay, so it feels like quite a complicated process, but it is about one line of code. The other thing I want to mention before we get stuck into actually writing code is workflows and recipes. So these are terminology that I guess is quite specific to tidymodels and might be a little bit unfamiliar. So when we talk about recipes, which is the package with the best hack sticker, okay? When we talk about recipes, we're talking about the series of pre-processing steps that you perform on your data before you fit a model. And then when we talk about workflows, a workflow is basically a way of combining that pre-processing with modeling and some post-processing steps as well. So for example, you could combine a recipe with a model. Okay, so what I'm going to do now is I'm going to run through some of those different steps in tidymodel. So we'll look at loading in some data, splitting our data into training and testing, and then creating cross-validation folds, building a recipe, and building a workflow. So it's going to feel like quite a lot of different steps, but hopefully it makes sense and it's not actually too much code here. Okay, so the first thing we want to do is load in our packages. So I'm going to load in the tidyverse first. And we're also going to load in the tidymodels package as well. Okay. We just load both of those. I'm also going to run another function here called tidymodels underscore prefer. Okay, so there are some functions in the tidymodels packages that have the same name as functions in other packages, including a couple in sort of base R. And all this function does is when you run it, it just says prefer to use a tidy model. So when you call that function, it's going to use the function from tidymodels with that name. Okay, so it gets rid of some of the little bugs or little errors or warnings you might get. All right, so let's load in some data. So I'm going to read in heart failure with read underscore CSV. So this is in data, and then you tab along, it's the heart failure one here. Okay, so let's just have a quick look at the data set first. Okay. Okay, so you can see here that our data set is not a huge data set. We got 299 rows and 12 columns. Okay, so each row is a different person, and then each column is some different characteristics. So age, sex, binary columns for whether or not they smoked, are anemic, have diabetes, etc. So the column that we're going to model is actually this column right at the end. Okay, the column that tells you whether or not someone died from heart failure in this sort of study. Okay. And what you can see here is that it's currently a numeric column here. Okay, so we have a double here. It's actually not a numeric column. It's zeros and ones. It's a binary column. So when we're using classification models, we need to make sure that our variable that we're modeling is actually a factor, not a numeric. So that's the first thing we need to do, and it's the only sort of pre-processing step we need to do at this point. Okay, so using mutate from dplyr, we can just convert that to a factor. Okay. I also recommend that even though this isn't a workshop about data visualization or plotting things, that you should probably have a look at your variables before you jump straight into fitting a model. Okay, so you can use things like the bar plot function from base R and look at the heart failure data set and how many zeros and ones do you have for the death column. Okay, so got about twice as many zeros and ones here. Okay, and it's also important to have a little look at the distribution of some of the numeric columns that we have. So for example, age. Okay, we can look at what does the distribution of age look like. Okay, and you'll see when we start thinking about other pre-processing steps for data, why it's important to know roughly the range of your data here. So we're going to start now splitting our data into training and testing data sets. So the first thing I'm going to do is set a random seed. Okay, so the way that the tidymodels function work is that they're sort of randomly splitting your data into training and testing. So to make sure that our work is reproducible, we can set the random seed. I always use the date because then I don't have to think about choosing what your random seed value is. But if you have a favorite number, please feel free. Okay, so we're going to use 3 different functions to split our data. So let's call it HF underscore split. Okay. And to split the data, we use the initial underscore split function. Now this has a couple of different arguments. There's 2 of them that I'm going to highlight other than the data. So the first argument here is going to be the data set that we want to split. The second argument is the proportion. Okay, so how much of your data should be in the training set? Now, the default, you can probably see it is sort of popped up there, is 3/4. Okay, so by default, 75% of your data goes into the training set, and you keep 25% for the test set. But you can choose whatever proportion you like, and it depends a little bit on what you're interested in terms of how much you care about it performing well on unseen data versus explaining the current data that you have, what proportion you choose. We also have the strata argument. So this determines sort of the proportion of particular variables in the training and testing set. So this is particularly important if you have a very imbalanced data set. Okay, so if we had very few ones in our data set, we wouldn't want to accidentally put them all in the training set or accidentally put them all in the test set. We'd want to make sure we had some in both. So that's another argument that you might use at some point. Okay, so we've performed the initial split, but if you have a little look at what this object looks like, it doesn't really look like data. Okay, it's just kind of information about how many observations are in the training set, how many are in the test set, and how many in total do you have. Okay. So to actually get the data back out, let's call it HF_train. And then we get training brackets, and then we pass in that split object. Okay. And we can do the exact same for the test set. So HF_test is equal to testing brackets HF split. Okay. And if you inspect either of these objects here, you can see this just looks exactly like our original data set, but we don't have quite as many observations there. Okay. So now we want to start thinking about how do we create those cross-validation folds. So we want to take that training data set, HF train, and create cross-validation folds. So we do that using the vfold_CV function. Right? I've always called it kfolds validation. Some people call it vfold cross-validation. It's the exact same thing. So it's a vfold_CV function. And the arguments that we pass into that is our training data set. Okay, so remembering that we don't want to be using our testing data set for any training. And then the number of cross-validation folds that you want to compute. Okay, so I'm just going to pick 10. The number you choose depends a little bit on essentially how long you want to spend training things and how certain you want to be that you're choosing the best values. Let's save that as an object. Okay. Okay. Now onto the sort of final pre-processing steps, if you like, is to actually build a recipe with tidymodels. So I'm going to call it HF_recipe. And see, this is why I like to have tidymodels, because everything is just so well named. If you want to build a recipe, you use the recipe function. Now, the input here is going to look quite similar to, for example, the LM function in base R that I'm assuming most of you are familiar with. Okay? So you can put in a formula. So what we want to model is the outcome is the death, and then tilde for a formula. So this is sort of y tilde x. Okay. Now I want to model all of the potential variables in my data set. So I'm just going to use a dot here, okay, to say use every possible column as a potential input in the model. Okay, what you could do here is you could do age plus sex plus smoking, for example, and type them all out. I'm just going to use dot because it's a kind of nice shorthand here. And I'm going to specify that the data set we're using here is the HF_train data. Okay. If I didn't want to do any other pre-processing steps in my data, we'd be done. But there's some other pre-processing steps that are kind of important for machine learning models. So one of them, the first one we're going to go through is converting any character variables to dummy variables. Okay, so you'll see we have one here. Our second column for sex, we have M and F. What we want to do is convert that to a dummy variable, which takes the values 1 or 0, depending on if you're in the sort of male column or female column. Okay. And for that, we can pipe our recipe into step underscore dummy. Okay, so it's the step that creates the dummy variables. And we specify, well, which columns do you want to perform that step on? One thing to note here is that there are different ways of writing models in tidymodels. And you can use the add underscore formula function, which does this sort of conversion step to dummy variables for you. I'm kind of a fan of being explicit about what transformations are happening to your data. So I tend to default to explicitly using the step dummy function instead. The other pre-processing step that I would suggest we apply for this data is that we normalize some of the numeric data. Okay, so we have a couple of numeric columns. Probably can't see the ones at the end. Let's see if we can have a look. Okay, so we have this column on the right here. So this is taking quite small values, sort of 0, 1, 2-ish. And then we have this age column, which you can see sort of between 40 and 100. So we have different numeric columns, but they're on completely different scales. And depending on what machine learning algorithm you're using, that can really affect the results. So what we want to do is we want to normalize those numeric columns and put them all on the same scale. Okay, so we want to normalize them. We use a step underscore normalize function. And again, we can pass in which columns we want to normalize. So it's going to be anything numeric. And in these functions, you can use the same sort of select helper functions that you do in dplyr select. Okay. So for example, you can use the colon operator to say, give me everything from this column to this column. Okay. And that's built our recipe. Okay. And the nice thing about this is that they're reusable. So you'll see as we go through the rest of the workshop, we can use this recipe repeatedly. So we're always applying the same pre-processing steps to all of our data. I would suggest that you have a little look at the step underscore functions in tidymodels. This is just 2 of them. You can also do things like PCA and these steps as well. And then our final sort of pre-processing step here is going to be to create a workflow. Okay, so I'm going to call it WF for workflow. And that is going to use the workflow function. And then after workflow, we can pipe in add underscore recipe, okay, with the name of the object that stores the recipe we created. Right. And so we have our workflow, and we're pretty much ready to start fitting models. Okay, so we split our data into training and testing. We have some nice cross-validation folds that we can use to tune hyperparameters, and then we have our recipe and our workflow. Okay, so it's now your turn to have a go at exercises. If you weren't coding along with me at the same time, you can still get a copy of something similar to the code that I've written in the examples folder. If you go into example underscore 1, you'll have something similar to the code that I've written if you want to use that as a starting point for exercises. But what I'd like you to do is if you go into the exercises folder and go into the exercise underscore 1 script, there will be some prompts in here. It's the same prompts that are on the slides. So if you load in the tidyverse and tidymodels packages, load in the exercises data, have a little look at the data, see what's in there. I think it's slightly bigger, slightly more columns than the heart failure data. Split the data into training and testing, choose whatever proportion you like, make some cross-validation folds, and then build a recipe and workflow. All right. If you get stuck there are solutions to the exercises that you can kind of use to run the code rather than, and maybe sort of run and edit the codes. Okay. You can also use the examples as a sort of starting point and edit the data set and the different arguments as well. Okay. So I will give you a chance to work through those exercises there. If you are getting stuck with anything, please do ask in the chat.
Yeah, Nicole, just wanted to chime in. There's been a few questions in the chat. I don't know if you wanted to wait
Perfect.
till after the break, the exercise time, or if you want to take some of those now. What would you prefer?
We can take some of those now.
Okay.
Fine.
There have been some answers already, but I'll check on ones that I don't think I have an answer yet. Martin was asking, how do you set the reference level for those step dummy, conversions you make in the step dummy function? If you have a multi-level character vector, how would you flag the
Ooh,
reference level
That
for that?
is a good question, and I cannot remember off the top of my head.
Okay.
But yeah, so I think yeah, that question is sort of when you change them into dummy variables, for example, male and female, that's not going to create two dummy variables, it's going to create one. And you always have a sort of base level class. You can, I know that for base R functions, you can set it in the options. If you set it in the factor level, okay, so at the moment, this column sex is it's just a character. So it treats it orders it in alphabetical order. If you set it as a factor, you can reorder it. I think it's usually the first one that's set as the base level. It's either the first one or the last one that's set as the base level. So if you reorder your factor and put whatever you want as the base level first, it should use that.
Excellent. And then one other one I flagged, there was I think some notation you had made about an interaction of the serum creatinine and time variables with a colon in between them. Do you mind explaining what that
Yes.
means?
Yes. So I guess this is something that's a little bit confusing when you're talking about models like that. It's not actually an interaction term. So this is how, if you're using dplyr selection, so when you select columns in dplyr, you can use this sort of colon notation. So rather than typing out the names of all of the columns from sort of serum and then creatinine, platelets, and so on, typing them all out, you can use the colon notation to say, give me all of the columns starting from here all the way up to this column here. So this is more about column selection than adding in interaction terms between variables here.
Okay, looks like we got another one along those lines. They're asking, can you use the index of the column, like 1 or 3 to 4 instead of the column names?
I would recommend against doing anything referencing by column position, because people add columns to stuff all the time. And if you rerun workflows on slightly different data and you go, oh, I want to model the third column, well, the third column could be anything if someone's added to the data. So if you reference by name, it means you're always kind of getting the variables that you think you're getting. So yeah, I would recommend going by column name rather than position. And with this sort of tidyverse framework, you don't need to put names in quotation marks, and it sort of pre-fills the names for you, so you don't really have to think as much about where anything is. There's one other question in the chat that I just noticed. It's probably a key thing. The target variable for exercise 1 is SAE. So I think it's the first column. So the target variable is the SAE. So that's serious adverse event. So it's whether, as a binary column, telling you whether or not someone had a stroke within the 6 months after their first stroke there. So yeah, when you're looking at the exercises data, it should be the SAE column that is your factor for output there.
And I did see a good tip from Libby about the setting the reference level inside the recipe. She's got a code snippet there that looks like that will work.
Yeah, perfect. Yeah, you can step re-level, so you can sort of re-level the factor there. Yeah.
So I'm not sure how much time you have left in this exercise. There are definitely more questions coming in, but we can defer them the next break or whatever you prefer.
I will keep them for the next break. And what we
Okay.
can do is we can move on to the next section where we're going to be kind of using some of the workflows. And I think that might answer some of the
Sure.
questions.
And I'll keep a
anyway.
record of them as well. So thank you.
Yeah, perfect. Thank you. All right. So yeah, as I mentioned, there are solutions to the exercises in the exercise solutions folder. Basically, what we're going to be doing now, the next sort of three examples we're going to be going through are three different models, and they all sort of use the objects that you've just created during sort of the first example and the first exercise. So the first thing we're going to look at, the first sort of model is lasso regression. Okay, but I want to go back a little step first. Okay, to talk very briefly about linear and logistic regression models instead. Okay, so most of you are probably familiar with the sort of LM function in base R that you can use to fit linear regression models. And similarly, if you want to fit logistic regression models to model sort of binary variables with those zeros and ones, you can use the GLM function, right? What happens if you have, let's say, 50 columns in your data set, right? How do you choose which 50 of those variables are important variables that you should actually put in your model? Okay, so that is the sort of next Zoom poll. Okay, how do you choose which explanatory variables are going to be in your model? Okay, do you use background knowledge, so you might know that something causes something else? Do you use sort of p-values and correlations between different variables? Some people also use stepwise procedures, so sort of iteratively adding a variable or taking variables out, or do you use some other technique? So let's see how people are currently choosing which explanatory variables to include in your regression models. So a lot of people use stepwise procedures. They tend not to work very well, particularly if you have a lot of variables. You can sort of end up going based on the choices you make early on with stepwise procedures. You can, end up with quite different models. So what you can do instead is use lasso regression. So when we fit standard regression models, what we're typically doing here is sort of minimizing the distance between the values we're predicting and the values we're observing. Okay. With lasso, okay, so least absolute shrinkage and selection operators, we still want to minimize the distance between the predicted and observed values. But we also want to minimize some penalty. Okay? And that penalty is lambda. So this is going to be hyperparameter times the sum of the coefficients. Okay? So we have coefficients with really big values. We want to kind of minimize those as well. So what this is going to do is if you have any coefficients that are kind of close to zero, the lasso regression is going to minimize them and sort of push them towards zero. If you have a coefficient of zero, then that variable is not going to be in your model. Okay. So to give you a little bit of an idea of what this kind of looks like, so as we increase on the x-axis, as we increase that hyperparameter lambda, the values of our coefficient shrink towards zero. Okay, so you can see, for example, this pink one up here, we have a very small value of lambda, our coefficient is 3, but if we increase lambda, it sort of gradually starts to push towards 0, and then eventually, at a high enough value of lambda, everything is 0. Okay. And so it's kind of one thing to note is if you pick a value of 0 for lambda, then that's just regular regression here. Okay. Although we're not covering it today, I also want to mention ridge regression because it does a kind of similar thing. Okay. It's not, you can't really use it for selecting particular variables, but it works in a similar way to lasso regression. So our hyperparameters, so remembering these are the parameters that we can't calculate from the data. We need to try lots of different values and see which one works best. It can take any value between 0 and infinity, so you can choose as high a value as you like. The higher the value you choose, the more coefficients are pushed towards 0. Okay, so you're going to get a model with fewer variables included. If you choose a lower value, that's something that's going to be closer to your standard regression models. Okay, and as I mentioned, choosing 0 is just a standard regression model. Since we're fitting our first model, we also probably should figure out how to tell if it's a good model or not. So we're working with classification models here. Okay, so we're trying to classify something. Is it a 0 or is it a 1? And there's lots of different classification metrics. I think one of the most commonly reported is accuracy. So this is just the proportion of the data that you predict correctly. Personally, I'm not a big fan of accuracy as a classification metric. It really doesn't work well if you have imbalanced data. Okay, so if you imagine you're building a model to predict whether or not someone has a particular condition, and let's say it's quite a rare condition, so maybe only 1% of people have this condition. If you just tell everybody that nobody has that condition, then your accuracy is like 99%. It sounds like you're doing really, really well, but actually you're doing terribly. Okay, so reporting accuracy for model is fine, as long as you're also kind of aware of any class imbalances and you're reporting other things. And it's one of the reasons, again, why I like tidymodels is because by default, it reports accuracy and the area under the ROC curve. Okay, so if you're not familiar with ROC curves, they look a little bit like this. So we put our false positive rate on the x-axis. Okay, so that's the number that we said were ones, but actually they were zeros. And we have our true positive rate on the y-axis. Okay, so this is the number of things this our number that we correctly positively predicted. So you can imagine the perfect situation is being in this top left corner here, okay, where you got everything right and you got nothing wrong. So the perfect model. So if you kind of look at this curve as, for example, the value of lambda changes, the closer this area is to 1, the better the model is. Okay. Although accuracy and the area under the ROC curve are what's reported by default, there are a lot of other metrics that you can get out of tidymodels really easily. So one I find myself using quite a lot is kappa. So it's kind of similar to accuracy, but it's normalized based on that class imbalance. So you don't get the problems with always just predicting the majority class, for example. If you have a little look at the yardstick vignette on metric types, it'll give you a kind of full list and an explanation of what each of the metrics are. Okay, so these metrics are all built into the yardstick package, which is used for model evaluation. Okay, so let's head back to Posit Clouds and go through some more examples. Okay, so we're going to go through a couple of different steps. We're going to start off by specifying which model we want to fit. Then we're going to tune the hyperparameter and then sort of fit the final model with that best value and then evaluate the model on our training data. So let's start off by specifying that we want to do logistic regression with the sort of lasso penalty. Something that I think is a little bit confusing here is that although we're doing lasso regression, we need to use the logistic regression function because it's essentially a special type of logistic regression. Okay, so let's specify the model that we're going to use for tuning the hyperparameter. Okay, so we can use call it anything you like. I've called it tune spec lasso, and that is going to be for the logistic underscore reg. Okay, and you can see that there's a couple of different arguments here. In tidymodels, there's sort of different what they call modes for how machine learning algorithms work. So they can be sort of used for classification, or they can be used for prediction. And the default for logistic regression has to be classification. Okay, we're trying to classify zeros versus ones. Okay, so we'll just leave that with the default here. Two other arguments we need to specify. The first one is the penalty argument. Okay, so this is where we specify the value of lambda. Okay, so what I could do is I say, I want to fit this model with a value of lambda is equal to 0.5. Okay, but I don't know that that's the best value. So what I'm going to do instead is use the tune function here. Okay, so this is just sort of specifying in this model, we're going to be tuning the lambda parameter rather than picking a specific value. And now we need to say that actually it's not just logistic regression, it's Lasso logistic regression. And so we need to set mixture equals to 1. Okay. And I think this was one of the things that's a little bit confusing, because nothing so far in this says we're doing Lasso regression. If you look at the help files for this, it does explain why you set mixture equal to 1. And it's because you have the logistic regression function can fit either ridge regression that I mentioned, or lasso regression, or a bit of a mixture of both. So when we set mixture equal to 1, it says just do lasso regression. So this is what's specifying that it's lasso here. And then we need to essentially tell tidymodels which package we're using to fit the model. Okay, so for that we use the set underscore engine function. Okay, and then what we do, the argument for this is going to be the name of an R package. Okay, so the R package we're going to use for Lasso logistic regression is going to be glm net. Okay, so that's kind of the package that implements Lasso regression for R. So I always find it a little bit tricky to remember what engines you could use to fit a particular model. And luckily, there's a nice show engines function, which will give you a list. So if we did show engines logistic underscore reg, okay, for the different combinations of logistic regression models you can fit in tidymodels, these are kind of the different packages that you could use. With logistic regression, it depends a little bit on what exactly, what type you're fitting. So now we need to tune the model. Okay, we need to figure out what that value of lambda should be. And what we're going to do is we're going to create a grid. So we're going to create a list of different lambda values, fit our model with each of those values, and then choose the best one. So let's make a grid. Okay, let's call it Lasso grid. And we're going to use the tune underscore grid function. Okay, so we need to specify 3 different things here. First of all, what model are we tuning? What data are we fitting it to? And what values of lambda do we want to try? Okay, so the first one, we're going to use the add model function, and we're going to use 2 arguments here. So one is going to be WF. So remember, that's the workflow that we created. So that contains the recipe. So which variables are we including, the pre-processing steps as well. And then we have the model that we've just specified here. We want to fit our data, we want to fit our model to the cross-validation data. Okay, so that's going to be HF_folds. And then the grid, okay, the grid argument is going to be the list of lambda values that we want to try. So it's going to be grid underscore. Now you have a couple of options here. I tend to default to grid regular. So that means we're going to try different penalty values, different values of lambda that are equally spaced on a grid. You could also use grid random if you just want to try random values, but my default is always to go for a regularly spaced grid here. Okay, so we pass in penalty brackets. Okay, so this, you can see that this sort of function that we pass in here is the same as the name of the argument in the logistic regression here. Okay, so that matches up. And then we can specify how many different levels do you want to try. Okay, so we could choose 50. Let's just go with 30. So this is going to try 30 different equally spaced values of lambda. Okay. So, turns out you have to actually run your code, right? And you can see that this is taking a little while here. Okay, it doesn't take too long in this case because we're not trying too many levels and our data set isn't absolutely huge. There are some other packages, the sort of do parallel package, which will run sort of fit each of these models in parallel rather than one after the other. That can kind of help you speed this up. In this case, I don't think we really need it. Okay. So let's choose the best value. Okay, so we say from this grid of values that we've just fitted, select the best. Okay. Now, what does best mean? What does it mean to say a model is better than another? Okay, in this case, we need to pass in a particular metric that we want to use to evaluate it. Okay, so for example, if we want to choose the value of lambda that gives us the highest ROC area under the curve, we can pass that in as an option here. You could also pass in accuracy instead. Okay, so let's save that value here. Okay, and then use that to fit our final model. Okay, and what you can do is, if you want to, you can inspect what that value is. Okay, so it's picking a value of lambda equal to 0.04 roughly. Okay, so for our final model, let's call it final lasso. It's the last time we're going to fit the model. Okay, and so we want to use the finalize workflow function here. It's the last bit of fitting this model. Okay, so again, we're going to say add model, the workflow that we have, our pre-processing steps. The model that we fitted, we want to fit the logistic regression model. But here, what we want to pass in is the sort of extra parameters we're passing in. So it's going to be the highest ROC. Okay, so it's going to be fit the model with that value of 0.04 here. Now we can evaluate our model on the training, on the test data set. Okay, so we can do last fit. It's the final fit of the model. So we're fitting final lasso to HF split. Okay, so here again, this feels a little bit confusing that it's the last fit of the model, but we're passing in HF split rather than HF test. So just kind of something to keep aware of. And what we can do is we can say collect metrics. Okay, so we fit the model to our sort of test train split, and we collect the metrics that we get out. Okay, and you can see that by default we get accuracy and the ROC area under the curve. Okay, so this model's not doing too badly. Okay, getting sort of 0.889, so doing fairly well. Now, the last thing I kind of want to mention about Lasso models is that you probably want to know a little bit more than just how well does it perform, eh? Particularly if you are using it for things like variable selection in regression models, you want to know, well, which variables ended up in the final model. It's a little bit complicated because unlike if you're doing standard linear regression, people tend to interpret the coefficients. Okay, so you say, okay, for every year that someone increases in age, their risk of whatever increases by a particular percentage. But because in lasso regression, we're always shrinking those coefficients towards zero, we can't kind of interpret the coefficients in quite the same way. So what we tend to talk about with these types of models is variable importance. Okay, so it's not, you can't interpret the coefficients in exactly the same way, but we can still figure out which variables ended up with sort of larger coefficients, which ones were more important. Okay, so let's have a look at that. Okay, so we take our finalized workflow here. Okay, and we're going to fit it to, we can look at the training data set. So when we were choosing our hyperparameters, which variables were coming out as most important. And we can extract the fit of that model. Okay, so we have extract fit parsnip function, and that's going to extract how that model was actually fitted. And we can pass that in to a really nice function, a sort of variable importance function. Okay, now this is one of the functions that is not in the core tidyverse packages. It's in the VIP package instead. So you can do VIP double colon VI. So the reason that I'm using namespacing here is because VI is the same name as a function that's in the sort of base R installation, and because it's not in tidymodels, it hasn't been picked up by our tidymodels prefer function. Okay, so it's one of those cases where namespacing is really, really important. Okay, so we can say use the value of lambda equal to highest ROC, the sort of value we picked. Okay, so let's kind of, oh, something's not gone right. So in this highest ROC, you can see it here, there's two columns. I need to specifically get the penalty column out there, okay? And what you get out is the 11 columns, the 11 variables. You have an importance score, and then you have a sign. Okay, so this is telling you, did it have a positive effect or a negative effect on the outcome? Okay, so you can see that 7 of our variables with the lasso regression have been pushed to 0. So this is kind of an automated way of saying we don't really need to include these variables in our model in order to be able to make reasonably accurate predictions. Okay, so you got time as one variable, having a sort of being the most important and having a negative sign, and then the sort of other 3 having slightly lower values here. Okay, so it is, like I said, kind of important to remember you can't interpret these importance values in the same way that you interpret coefficients in regression models, but you can still use them to say, okay, this variable is more important and has a bigger effect on the sort of predictions than other variables. Okay, so it is once again your turn to have a go at some exercises. So if you go into the exercises folder and go into exercise _2, if you fit a logistic regression model using the logistic reg function, tune the hyperparameter, choose the best value, fit the model, and evaluate it. Okay. If you got stuck on the first set of exercises, you will need the sort of objects that were created. So if you go into the exercise 1 solutions, you can kind of just source this script and it'll create all of the objects that you need. Okay. So I'll give you a little bit of time to work through those, and I will come back and answer some questions in the chat in the meantime.
All right, Nicole, would you like me to surface some of those to you now, or do you want to handle that in the chat yourself? How would you like to do it?
Yeah, if there's any in particular that kind of stand out, that'd be great.
Yeah, absolutely. There was going back to the concept of splitting data sets. There was a question about, does the splitting function account for class imbalance and maintain that proportion in the split, such as in the caret package? And in more general terms, if you have a large enough sample size of a large imbalance in the outcome, would you recommend subsampling the larger class?
That's a very good question. I'm going to go with the classic answer of it depends. So it depends a little bit on what exactly you're trying to predict, whether things like subsampling make sense. So for things, I'm trying to think of an example off the top. So some of the data I've been looking at is trying to predict from sort of sound recordings which people have heart murmurs. Right? And that's obviously it's a minority class, right? Very few people have them. So it's really important that we are able to predict that minority class well. And so subsampling and sort of oversampling from that minority class would make sense. But if you're actually trying to figure out what the kind of average is, then subsampling doesn't make as much sense. So it depends a little bit. Whether or not you use subsampling depends a little bit on what you're actually trying to do. It's not, if you have a class imbalance, definitely subsample. It's think about, is that minority class your kind of target, or are you more interested in the average? If you are more interested in the average, then sort of oversampling the minority class doesn't make as much sense, I don't think.
Okay, and then there were a couple other ones that I think, yeah, could use your help with. One was asking if the model has already been fitted during the tuning step of your analysis pipeline, can we not just extract it directly rather than fitting it again in your step that was with the finalized workflow part of the function?
I'm not entirely sure. You're right, it does seem like something you probably should be able to get out. If you sort of look at the lasso grid here, you can sort of see the different fits. It's never something I've done. And I think in terms of the way your code looks, I do think it is a little bit cleaner if you sort of extract that value and refit it. Yeah, the answer to that is as I'm not entirely sure, I would have to go and double check. I guess one of the reasons you might want to do that is if it takes quite a long time to fit your model. You know, if you fitted it n times, and do you want to fit it n+1 if that increases the time it takes? I've never found that to kind of be a barrier to refitting it once, and it means you can kind of save that final object somewhere as well and you don't have to save all 30 models. Once you pick that best value, you can kind of drop those and just keep the one you need. So I don't know if you can. I imagine there's probably a way to do it. It might be a kind of hacky solution, but I've never found a reason for doing it.
Yeah, that's kind of been my limited experience as well. This is another interesting one. What are the advantages and disadvantages of the lasso method as opposed to, say, regular logistic regression? And could you use lasso to select variables and then use those in a standard regression model?
Yeah, there's advantages and disadvantages. So I think advantages are that it is automatic sort of variable selection. We know that things like stepwise procedures don't tend to work very well. And using sort of, domain knowledge or background knowledge of what might cause something else is useful if you know those things. But sometimes you're kind of fitting regression models as an exploratory step because you're trying to figure out what does cause something else. So you don't always have the background knowledge. So Lasso can definitely point you in the right direction. And I think that's particularly true when you have a lot of different columns. Okay, then in the data sets we're working with in these examples, we've got sort of like 10 columns. It's kind of easy, it's kind of doable. But if you have, hundreds of columns, anything that's manual, just it's infeasible to do it. So I think that's one of the big advantages. The disadvantages are that it is sort of harder to interpret. You can't interpret coefficients in the same way. And there are kind of attempts, I think someone else has posted in the chat as well, sort of like adaptive lasso, which kind of tries to select the variables and push them into a standard regression. So it's definitely something you could do. Again, it depends on what you want. So I think in terms of if it's about making predictions and making accurate predictions, then I don't think you need to put it into a standard regression with just those variables. If the lasso is creating accurate predictions and that's what you care about, then just use that. If you're more interested in sort of inference and figuring out what causes what, then that's one way to go. There are also sort of causal machine learning methods as well that could kind of work there as well.
Excellent. We may take one or two more before you head on out.
Yeah.
There's a great question about, can you get variability metrics around variable importance, back to your earlier example, such as what we can get when we do traditional confidence intervals in the typical least squares regression?
Yes. So I believe you can. The thing with sort of a variable importance is it changes quite a lot between the different algorithms that you're using in tidymodels. So for some models, you will be able to get like variability around the importance. For other models, it's kind of trickier. And then for other models, again, you don't really have such a thing as variable importance. So yes, in some cases, I think is the answer to that question.
All right, excellent. We, like I said, they're coming fast and furious. But
Yeah.
as you mentioned, as I mentioned earlier, I'm recording all of them, and like you said, you may do a blog post about this afterwards. We're getting a lot of great engagement here.
Yeah, perfect. Okay, I'm aware of time, so what I'm going to do is I'm going to jump back in to the slides and go into the sort of next model now. There are solutions to exercise 2 in the exercise solutions folder as well if you need them. If you did manage to get to the end of exercise 2, feel free to share with us what sort of ROC you got from your lasso model. Okay, did it do quite badly, less than 70%, between 70 and 80, 80 to 90, or 90 to 100? Okay, so we're going to move on to a slightly different type of model, but which is still working with the same data and still trying to predict classes of zeros and ones. So we're looking at random forests, and in order to make a forest, you need some trees. So we are going to start by thinking a little bit about decision trees. Okay, so these are basically tree-like models of decisions and the possible outcomes or consequences from those decisions. Okay, so for like a really simple example, you might decide, okay, should I walk to work today? And the questions I might ask are, is it raining? Yes or no? And then if it is raining, I might want to check whether or not it's windy later, and then that will determine whether or not I walk or don't walk to work. Okay. So if you think of each of these white boxes here as essentially being like variables, okay, so you kind of start at the top and then you work your way through the decision tree based on the values that different variables take. Now, what random forests do is essentially it's an ensemble method that combines lots of these decision trees. And they can be used for classification or regression problems. Okay, so we start with our data set and we put it through a decision tree, and it comes out and it says, okay, this one's a 0, for example. We put it through a second decision tree and it says, okay, actually this is a 1. put it through another one, and so on. Okay, so if we're doing regression problems, what you'd get is an average across all these decision trees. If you're doing classification, it's what one was the sort of majority. Okay, so did you get mostly zeros or mostly ones? Okay, so that's how random forest works. Now, we have quite a few different hyperparameters for random forest. There's a lot of different things we could change here. Okay, so the first kind of obvious one is the number of trees. So how many different decision trees should you fit for your model? We also, in tidymodels, is sort of try. This is a number of predictors that you want to randomly sample at each split when you create the tree models. Okay, so for each decision tree, I'm going to randomly sample X different predictors. Okay, and then there's also sort of min n, so the minimum number of data points in a node that are required for the node to be split further. Okay, so you might go down, so you just have sort of one in each split, or you might say, actually, I need to have at least 5 in each node. Okay. So these are the kind of 3 hyperparameters that you can tune. So let's have a little look at how we actually do that. Okay, so heading over to example number 3. Okay. And I'm hoping what you see in this example is that it's actually, the process is very, very similar to Lasso regression. Okay, we want to specify the model, tune the hyperparameters, fit the final model with the best value, and then evaluate it. Okay, so let's create an object, tune spec rf, rand underscore forest. Okay, so rand underscore forest for random forest. And then we have our 3 different hyperparameters here. So we have mtry is equal to tune again. So same as when we're using that penalty in Lasso regression, we're using that tune function to say it's going to be one of those hyperparameters we tune. We can also set trees. Okay, you don't have to tune every hyperparameter. You can mix and match, tuning some and sort of specifying others. So what I would normally say is that for, at least for exploratory work, 1,000 trees probably works kind of well. In the interest of time and getting our code to run reasonably quickly, I'm only going to do 100 here. Okay, so I'm using 100 for examples, but probably definitely use more in practice. Okay, and we can say min n is also going to be tuned as well. And here we're going to use set mode. Okay, so this is something we didn't have to do for logistic regression because the sort of default mode for logistic regression is classification. Because random forest can do either classification or regression, essentially, we need to tell it we're doing classification here. And then we have set engine as well. Okay, so, and again, this is kind of going to be the package that's actually the name of the package that's actually implementing the random forest. And for this is the ranger package here. Okay, so that's how we've specified our model. Specify which parameters you want to tune or which values they should take. Set the mode to classification and which package are you using to fit it. And then we're on to tuning hyperparameters. Okay, now you can almost copy and paste the logistic regression code we had earlier if you like. Okay, so it's going to look very similar. We have tune underscore grid. We have add model. It's our workflow. And here we say tune spec random forest. The resamples we fit it to are the HF underscore folds. Okay, our cross-validation folds. We can do grid is equal to grid regular again. And then in here, we can specify, again, what functions, which arguments we're adding into the grid. Okay, so we have mtry function. Okay, so again, remembering that the names of these functions match up to the names of the arguments here. And you can specify a range of values. Okay, so remember that mtry is the number of predictors that you want to sort of use in each decision tree, and that's kind of randomly sampled. So you can specify a range. Okay, so for example, I could say it always has to be between 5 and 8, for example. Okay, I want to have at least 5 predictors in my model. We also have min underscore n function. And again, it's the same thing. It's the sort of number of observations in each sort of node split. So it's going to be a range again. I'm just going to leave it as the default here. Okay, so the default is between 2 and 40. Okay. And again, we specify how many different levels we want to try. I'm going to pick quite a small number so that it tunes in a reasonable amount of time. Okay. You can see that this one's taking a lot longer than the Lasso regression. Part of that is because random forests are kind of, they take a little bit longer to fit. But we're also tuning, multiple hyperparameters rather than just one. It is sort of actually a two-dimensional grid here. And then the rest of the code is very similar. Okay, so we can choose our highest ROC value for the random forest. Okay, so take the values from RF grid, pipe that in to select best. And specify the metric that you want to use to define what best is. Okay, and you can see here, right, we have sort of multiple values here. Okay, so it says the optimal value for mtry was 6, and the minimum number for n came out as 40. Okay, I do think it's always useful to inspect what these values of hyperparameters are, particularly when you're specifying things like a range. Okay, in case it comes out near the end of the range you've specified. So for mtry, it's probably fine-ish. Okay, it's come out as 6, which is kind of in the middle. But for min n, we use the default of being between 2 and 40, and this is said the best value here is 40. So what we might actually want to do is go back and retune that and set the range a little bit bigger. Because maybe the optimum is 41, but it just wasn't in the range of values we tested. Now that we've figured out what the optimum values are, we can again fit that final workflow with that best value. So we can do final underscore rf finalize. Finalize workflow, add model again with workflow, and the tune spec RF. Okay, so the model we specified, and then the highest ROC value. Oh, should be a comma. There we go. Okay, and we can evaluate it in the same way again. So you have last bit, final RF, HF split, and then collect underscore metrics. Okay, and you can see that now we have an ROC of 0.95. So that's doing a little bit better than the Lasso logistic regression here. Okay, it's kind of an improvement there. I quite like visualizing results rather than just sort of looking at a table of ROC values. And quite often what people do for binary classification is create confusion matrices. Okay, so it tells you the number of sort of true positives, false positives, and so on. And we can do that with the output from last fit. Okay, so we have last fit, final RF, so HF split. Okay, and here, rather than doing collect predictions, rather than doing collect metrics, we do collect predictions, and we pipe that in to conf mat, okay, to get our confusion matrix out. And we do need to tell it which sort of outputs, what are the observations and what are the predictions. Okay, so it's going to be death, so the column from our data set, and then .pred class is the output from collect predictions. Okay, so this gives you a nice little kind of printed confusion matrix here. Okay, so you can see that ideally we want these to be diagonal. Okay? We always want zeros to match up with zeros and ones to match up with ones. The nice thing about tidymodels is that you can put this into an autoplot function and you get this, okay, which is probably is not what your standard confusion matrix looks like. People tend to always draw them as sort of square grids, but this kind of helps to highlight that you have class imbalances. Okay, so you can see that the sort of width of the columns are based on the size of the classes relative to each other. So it can be really useful for visualizing these confusion matrices and seeing if they are actually diagonal. All right. That brings us to the end of random forests. The examples code, again, is in the examples folder. And it's your turn to have a little go at some exercises again. Okay, so if you go into exercises 3, okay, so what you're doing here is specifying your model, tune your hyperparameters, fit it, and evaluate it. Okay, you can either use the sort of example 3 code and copy and paste it and change it for the exercises data set instead, or you could start from the Lasso Regression code and sort of see how much of it do you actually have to edit in order to fit a completely different model. And hopefully you'll find that actually it's very similar and you don't have to change very much at all.
All right, would you like to take another batch of questions, Nicola, or?
Yeah, absolutely.
Okay, I've seen this pop up a couple times, this current one. In the examples you were showing earlier, you've been leveraging HF_split in a lot of your remaining steps. There's been some questions about why haven't you been using HF_test in those various steps?
Yes, so when we're fitting it up here, sort of in the tuning, we're fitting it to the cross-validation folds to get the best values of the hyperparameters. We haven't actually fitted it to the full training data set yet. So in terms of other parameters and actually figuring out what is the final model, we haven't fitted it to the training data set at all, to the full training data set when we're just tuning it. So that's kind of why we use HF split here. It sort of fit the final model to the training data set, figure out what any other coefficients might be, and then evaluate it on the test set. So it is a little bit confusing, I agree, because it feels like you've fitted it to the training data set many times. Actually, we haven't fitted the model to the full training data at all yet. So we want to fit the whole thing with those best values and then evaluate it on the test set. And HF split is kind of a nice way of doing that because it has that split between both training and test.
Excellent. And then you were also making use of the last fit function right there in that snippet. There have been some questions about some clarification on, is that taking care of applying some of the pre-processing steps you flagged earlier on the testing set, or is that not relevant here?
It's doing everything to both data sets. So if you kind of work your way back through, so we have this last fit function. The first argument is this final RF, which is the finalized workflow object. And you can see that what we've got in here with the add model is we have this workflow object here. Okay, so our original workflow contained the recipe, which had the recipe function, all of our pre-processing steps, so those like step dummy, step normalize, then the workflow, finalize workflow, and then we push that into last fit. So it is sort of doing all the steps here pushed in. So any pre-processing that you do to your training data set to fit the model, it's making sure that the same pre-processing has been done to the training set, the test set as well.
Excellent. There may have been some clarification when you were running the tuning of the grid parameters. Is the Ranger package required for some of that? Because Libby was saying she had to install that in order to get her grid to run in the example.
Yes. Yeah. So you will definitely need the Ranger package. So the Ranger package is is a package that actually fits the random forest. And when we're doing that tuning grid, we're fitting lots of random forests multiple times. So you will definitely need the Ranger package installed. One thing I maybe should have mentioned at the start is that in the files, if you sort of clone the project, there's a setup.r file. If you clone the project from sort of my version of it, it should already be installed. But if you do want to run this sort of on your own laptop, these are the packages that are kind of required to run all of the examples. Okay, so you have GLMNet, VIP, Ranger, and Current Lab, which we'll come on to as well.
Yeah, and I believe you'll probably be touching on this in the remaining sections, but there is interest in seeing how this will actually be used to make predictions on new data. I assume that's coming up next.
It might be.
Okay.
Yeah, you can definitely sort of pass in additional data as well. And yeah, depending on what you're doing, sometimes people if you have new data, that is also essentially a test set because it's completely unseen data that hasn't been used in any of the model validation.
Excellent. Now this one's going to be a bit higher level, and if you want to take it, that's fine. But there's been some questions regarding, what are some of the advantages, in your opinion, of the tidymodels framework as opposed to some of the more traditional modeling stacks, such as in Python with scikit-learn? I don't know if you had perspectives on that.
Yes, definitely. I think one of the benefits is if you're already using R for everything else, then it's much easier to continue using R for machine learning. There are packages that let you run Python code from R. Of course, we could still use Python to fit models. But I think if you're already working in R, then continuing to work in R for machine learning makes a lot of sense. I also think that tidymodels feels very user-friendly. Things are sort of named well. It's kind of like the sort of tidyverse in general is named well. It seems to be very user-friendly and quite beginner-friendly. So I do think it feels like a nice way to do machine learning. And I'm quite a big fan of ggplot too, and it means I can directly sort of visualize results of models in those packages instead. I think it's what I've sort of done in the past and seen people doing is you might do your exploratory data analysis or pre-processing in R, output your nice clean data to Python, and then bring it back into R to visualize it. And it's like, well, actually, you could do the whole thing in R. I think there is a little bit of a misconception that if you want to do machine learning, you have to use Python. And I don't think you have to. You can, but you don't have to.
All right, you got another one that just came in, going back to the pre-processing that's run on your training and test sets. They're asking if you feed the parameters from the training side of it to help process the test. And the example they gave is when you normalize a variable in the training set, does that normalized test set have the mean and standard deviation different from 0, if that makes sense?
I'm not 100% clear on
Okay.
the question. I think it was if are you normalizing the training data separately from normalizing the test set is I think what the question's kind of getting at. And I don't believe you are. You're kind of normalizing the whole data. Yeah.
Okay, great.
Okay. All right,
I think we're pretty
let's-
much caught up. So yeah, let's keep going.
Yeah, perfect. All right, what we'll do is we'll go over the kind of last set of the last model that we're going to fit. And then we'll have, I guess, a little bit more time for questions at the end. So the last thing we're going to look at is, again, a different type of model that you can use for binary classification. So we're going to look at support vector machines, or SVMs. Essentially, in very, very simple terms, SVMs essentially draw a decision boundary, draw a line that best separates two groups. Okay, so if you have this really simple, this really nice little example here. Okay, so you have a bunch of orange dots and you have a bunch of green dots. And I said draw a line that separates these two groups. You probably draw something like down here, right? Something like that. And then you kind of have this question, well, what line's the best line? Okay, I could draw this sort of solid line, a dashed line, or the dotted line. Okay, so you might be starting to thinking when I'm saying, well, which line's the best line? That's where our sort of hyperparameter tuning is going to come in, is to help us figure out which line is best. Okay, and then after we've drawn our line, so let's say we went with the solid line right down the middle. If we had some new data points that came up, let's say up here, that would be put into the green group here. Okay, so the line sort of defines the two different classes. And then the next question is, well, what sort of line should you draw? And it turns out there's a whole bunch of different lines you can draw. Okay, so when we're talking about SVM, we tend to talk about these in terms of kernel functions. Okay, but they're effectively controlling what type of line you're drawing. And in tidymodels, we actually have different functions for these different types of kernels. Okay, so if you use SVM linear, that, at least in 2 dimensions, is going to be drawing straight lines. Okay, so here differences are sort of blue and pink that defines the 2 different classes. And you can see there's a bunch of parallel lines here. We also have a polynomial. Okay, so SVM poly. And you can see these are drawn kind of curved lines in between them. Okay, so you can have different degrees of polynomials to draw a curved line in between the 2 different groups. And then thirdly, you have what we call radial basis functions. Okay, and you can see that these are a little bit less like lines and kind of more like sort of circles or contours. Okay, so trying to group these in a sort of radius here, and you can see the lines kind of diverge a little bit. Okay, so they have these different types of kernel functions that you can choose. Now in SVMs, again, like most of our machine learning algorithms, we have some hyperparameters. Okay, so the kind of, I guess the most commonly talked about hyperparameter for SVMs is cost. So it's a kind of cost function. And this is the trade-off between fitting the data really well and not overfitting your data. So if you choose a high cost value, that emphasizes fitting the data, the training data very closely. If you choose a lower value of cost, that prioritizes something more general and avoids overfitting. Kind of related, you also have gamma, which controls the shape and sort of smoothness of the decision boundary. Again, sort of higher values, more flexible boundaries, lower values, simpler boundaries. There might be other hyperparameters depending on the choice of kernel. Okay, so for example, if you choose to use a polynomial kernel, you have to decide what's the sort of maximum order? Is it squared? Is it cubed? Is it degree 4, or so on? Okay, so this is one of these cases where there might be additional hyperparameters or additional choices you have to make. So let's head back to Posit Cloud and have another look at some examples. So again, you'll see that this is really similar to the Lasso Regression and the random forest code. Okay, so let's create our tune spec SVM object. Okay, so I'm going to use a radial basis function. So it's SVM underscore RBF. And cost is going to be equal to tune. So I'm going to tune the cost hyperparameter. I'm going to leave everything else with the defaults for now. Okay, so we'll just focus on tuning one hyperparameter. Again, we need to set the mode and the engine. So we can do set mode classification, okay, and set engine. Okay, here it's going to be Kern Lab. Okay, the engine that you choose is going to depend on whether it's classification or regression, but it's also going to be dependent on the choice of kernel. Okay, so if you choose SVM linear, it'll be a different engine here. And again, just as a kind of reminder, you can do show engines, SVM, RBF. Okay, and that tells you the different ones there, and you can see the different packages that you can use for classification or regression depending on the mode and the kernel function. Okay, so if you decide to use a different kernel function in the exercises, you might need to install a couple of additional packages. So let's make sure I run that code, and then let's fit lots of values again. So create SVM grid is going to be tune grid brackets as model workflow or specified model. Tell it that we're fitting the resamples as being those cross-validation folds. And then our grid is going to be grid regular cost. And let's just set levels equal to 30, for example. Yeah. So we want to fit lots of different values with our radial basis functions. Yeah, it's taking a little bit of time here. So what I would suggest is that if you're doing this in practice, you probably want to be using more levels or sort of more variables. You're probably going to have bigger data sets in practice. So that do parallel package is probably going to come in handy if you're doing machine learning in a kind of more practical setting. So let's once again choose our best value from that grid that we created and into that select best function. Okay, so let's have a little look at what value it picked. Okay, so it's picked a cost value of 0.02. And then we can once again fit our final SVM model. So you could do finalize workflow as model, workflow tuning spec SVM and highest ROC SVM to fit the final model. Okay, and then we can evaluate it as well once again. Okay, so hopefully this code is starting to feel a little bit repetitive and kind of familiar, that even though you're fitting models that in practice are entirely different, the process of writing the code and actually fitting the model when you're using tidymodels is really similar. Okay, so we can do collect metrics. One thing I want to kind of point out here is that so far when we've been looking at the different metrics, we've just kind of been looking at the defaults, the sort of accuracy and ROC. You can specify different metrics. Okay, so you could do metrics is equal to metric set function. And then here you just put in the names of different functions. Okay, so if I want to keep ROC and accuracy, I can put them in here. But I can also put in different metrics from the yardstick package. Okay? And then when you run last fit and collect metrics, you don't just get the defaults, you get these additional metrics as well. So you can specify exactly which metrics you want. The default metrics you get out depends on the mode you've set. So if you're doing regression models, for example, you might want to look at things like root mean square error, or sort of absolute error, for example, and you'll get those accuracy out by default instead. Okay. I think we just have time for you to have a go at the kind of like last set of exercises. So if you want to hop into exercises _4, doing something very similar to the last set of exercises, specify that SVM model, tune some hyperparameters, fit it, and evaluate it if you can. Right. And again, you can start from the random forest code, for example, or you can start from the example code if you want a starting point.
Don't worry, have any new questions right now, but there was a great comment I wanted to surface to you. Neil saying that the repetition that you're showing here is the beauty and simplicity of this whole ecosystem. It makes it so much easier to explore different models and is very intuitive. So that seems to line up with what you were saying earlier about why you're a big fan of tidy models.
Yeah, definitely. And if you have, if you're fitting the sort of, it's one of those things where you start seeing repetitive code and you think, well, if I'm repeating code, I should probably write a function. And because it is so repetitive, if you want a particular set of metrics and you want to do a particular outputs, it's really easy to sort of wrap some of the existing tidy models function to give you what you need for your specific workflow, and you can fit lots of different models using your own nice little wrapper function. So yeah, it's nice for a learning process, but also for writing functions is much nicer than copying and pasting code.
Absolutely.
I was going to pick up on a question from the chat from a little while ago, looking at whether the models work the same way with a time series. So I guess the first difference from this would be sort of right back at the start when we did that initial split. So when you're doing an initial split for non-time series data, you can randomly pick any observations you like for training and testing. But when it comes to time series, if you pick random observations, then you're going to mix them up all in the time. So what you need to do is sort of split it in a particular way. And there is a sort of function. If you type initial split, in fact, let's do that. Yeah, initial _time_split is it's used specifically for splitting your data in a way that preserves the time ordering of observations. And then you can use various models based on that as well. And like some of the comments are saying, you might need to build some of your own features. So things like if you have autocorrelation in your data, then using things like lagged values as columns can be really useful here.
And if I recall, I think, yeah, that addition of the initial time split and some other helpers is fairly new in the tidy models ecosystem, because I don't believe they addressed time series early on, if my memory serves me correct.
Yeah, I think that's true. I think the initial was sort of let's get the kind of more general sort of simpler models into tidy models first, and then time series was added later. I'm not sure what the link up between sort of tidy models and things like sort of Fable and the sort of the forecasting packages that go with that is. I should probably have a little look at that. But yeah, I think again that kind of fits within the nice sort of tidyverse framework of doing things. So if those two packages were talking to each other, that would be wonderful for time series analysis.
Yeah, and yeah, this is going back to an earlier exercise. Maybe you'll touch on this later, I'm not sure, but there was some questions about the model that you asked everybody to create an exercise to, how that would be run to actually predict the SAE outcome that you mentioned earlier.
Yeah. So there are sort of predict functions. So if you use sort of any sort of forecasting or predictive modeling in base R, you use the predict function. The predict function also works within the sort of tidyverse framework as well. So you pipe your kind of model into predict alongside your new data, and it will output your predicted outcomes as well. And I believe that's in terms of like collect metrics and collect predictions, that's essentially wrapping around that and sort of tidying up the output as well. So yeah, the predict function has a version for tidy models output as well. We are coming near to the end. So there was just a couple of kind of additional things I kind of wanted to link people to. Kind of like I said at the start, machine learning is a massive topic. Tidymodels is a massive suite of packages, and I think there's a sort of blog post came out literally yesterday with another update and some changes to tidymodel. So it is sort of constantly evolving, and we haven't covered all of it today. So I hope you kind of been inspired a little bit to go and look at some other machine learning models and other tidymodels functions. I think as well as when you're thinking about machine learning, learning about models and learning how to write code is great, but it's also important to think about things like ethics and sort of bias and discrimination. We talked a little bit about imbalanced classes, and sort of most machine learning models, in fact, most statistical models tend to try and predict the average, right? That's what they're for. So kind of being aware of some of those things, and topics like explainability and validation are important as well. If you want some additional resources to go away and look at tidymodels, the tidymodels documentation is really good. It's got some really nice examples. And a lot of the time it has an explanation for the algorithm or the process or the metric. The explanation tends to be sort of tied to that as well. So it's really nicely documented. I'd also really recommend this book, Tidy Modeling with R. It kind of goes through the end-to-end process of building machine learning models within tidymodels. I'm a massive fan of Julia's blog. So Julia uses the Tidy Tuesday data sets and sort of every week runs through sort of start to finish. Here's a data set. Let's fit some models. Let's evaluate them, and goes through the whole process on lots of different data sets and lots of different models. So if there's something specific you're looking with, definitely have a look at Julia's blog. The other thing that's not in here, but I think is probably worth mentioning is the vetiver package. So a lot of the time when we've been talking about machine learning models, we're running them in our own little cloud space, or we're running them on our own laptops. The vetiver package is really nicely integrated with tidymodels, and it helps you to deploy those models. So get them off your laptop and get them sort of out into the world where people can use them. So tidymodels has a nice integration with vetiver, and I guess that kind of an extra answer to the question earlier is why should you use tidymodels to do machine learning? There's one of the reasons it's really easy to deploy those models as well if you use this kind of framework. Yeah, and just kind of a final reminder that the workshop resources are up on GitHub, and the slides are available online, and they'll stay online. And yeah, I guess the recording will be available in a few months if you want to come back to it and work through it. But yes, thank you very, very much for the invitation. I really enjoyed running the workshop, and I hope you found it beneficial. I'm happy to stick around for a little bit if you have any questions.
Well, we're seeing a lot of thank yous and very nice messages in the chat, Nicola. So yeah, this has been extremely, extremely fun for me to be an observer on this and seeing the engagement here. You've been very, very helpful. The examples I think have been really clear, and the best of all, for all of you that want to play with this more, all the materials are online. It's like all the other workshops we have here. Yeah, I'm already seeing some also great recommendations to other resources, some of which you've already mentioned, but it does sound like we have a lot of our audience wants to continue their tidymodels learning journeys here.
All right. Also, I'll just mention real quick for the certificates for today, when you exit, you should see a form pop up. And so if you'd like to get that credential, please fill that out. If you don't see that for whatever reason, just shoot an email to info@rnpharma.com, and we can get that added for you. So thank you so much for coming. We've got an awesome list of 2 more workshops for today, one with Will Landau for targets. Then we also have a Quarto workshop with Devin Pasteur, and then workshops the rest of the week, and then the workshops and the conference next week. So feel free to join the next few sessions and join the conference next week. Thank you, Nicola and Eric. This was phenomenal. I had such a great time listening and watching. And Nicola, you have such a great demand of the environment. I was just impressed at how awesome that was. So thank you so much. And for everyone that came, we will see you later.